The next set of formulas we're going to look at are the so-called double angle formulas. These give us a way to express the sine, cosine, or tangent of twice an angle in terms of trig values of the angle itself. So the first one we have is that the sine of 2 theta is 2 times the sine of theta times the cosine of theta. We have cosine of 2 theta is cosine squared theta minus sine squared theta. And tangent of 2 theta is 2 times the tangent of theta divided by 1 minus tangent squared theta. And these just come from the sum formulas for sine, cosine, and tangent. So we can use the fact that the sine of 2 theta is the same thing as the sine of theta plus theta. So really, we're just adding theta to itself, so we can use a sum formula. And when we expand it out, we're going to get something that equals sine theta times cosine theta plus sine theta times cosine theta is 2 sine theta cosine theta. Similar for cosine and for tangent. So I'm going to start out with 2 examples. These are sort of the 2 main examples we'll see of just the double angle formula. The first is if we're using the formula from right to left, where we have numerical angles plugged in. So here we have 2 times the sine of pi over 8 times the cosine of pi over 8. Of course, we don't have a method yet to find sine or cosine of pi over 8. So what we'll do instead is note that this looks like 2 sine theta cosine theta, okay, which is the sine of 2 theta. And therefore, 2 times the sine of pi over 8 times the cosine of pi over 8 is the sine of 2 times pi over 8, which is the sine of pi over 4, which is 1 over the square root of 2. Okay, so that's all there is to it. We're not going to use the double angle formula to find the sine, cosine, or tangent of any specific angles, because if you think about the angles whose sines and cosines and tangents we know, things like 30 degrees, 60 degrees, 45 degrees, 90 degrees. If you multiply any of those angles by 2, you're going to get another angle whose trig value you know. So for example, sine of 45 degrees we know, tangent of 45 degrees we know, cosine of 45 degrees we know, and if we multiply that angle 45 degrees by 2, we'd have the angle 90 degrees, and we know the sine, cosine, and tangent of 90 degrees. So the double angle formulas are not tremendously useful in that regard, going left to right with specific numerical angles, but they are useful going right to left. And the double angle formulas will also set up the half angle formulas, which are going to be useful for us. Okay, so now let's turn our attention to this second problem. Here is a question where we're going to be using the trig formulas from left to right, because we're given some information about the angle, but we're not told the angle itself. We're told that the cotangent of theta is equal to 10, and theta terminates in the third quadrant. We want to find the sine, cosine, and tangent of 2 theta. Okay, so what we need to find are the sine, cosine, and tangent of theta. So we need to find the trig values of theta in order to find the trig values of 2 theta. Okay, but this is a problem we know how to solve, because we're told one trig value, and we're told a quadrant. So we're told that the cotangent is 10, and we terminate in the third quadrant, so there's theta. Cotangent is x divided by y. That's going to be equal to 10. Remember, in the third quadrant, x and y are negative. So x is going to be negative 10, y is going to be negative 1. Cotangent x over y is 10. And then our hypotenuse, our r, is going to be the square root of negative 10 squared. X squared is 100. Y squared is negative 1 squared is 1. So we're going to have 100 plus 1 is 101. And therefore our hypotenuse will have length square root of 101. And this triangle is all we need to finish our problem, because now we have the trig values of theta, and we can use those to get the trig values of 2 theta. let's start out with the sine of 2 theta. Okay, so the sine of 2 theta is 2 sine theta cosine theta. Okay, and looking at our right triangle, we note that the sine of theta is -1 over the square root of 101. Okay, and cosine of theta is -10 over the square root of 101. Okay, so that's going to be 2 times -1 times -10 is positive 20 over square root of 101 times square root of 101 is 101. Okay, that's to say the sine of 2 theta is 20 over 101. Now if we do the same thing for cosine, cosine of 2 theta is cosine squared theta minus sine squared theta. And cosine of theta is -10 over the square root of 101. Sine of theta is -1 over the square root of 101. So that's going to be equal to 100 over 101 minus 1 over 101. Okay, so -10 squared is 100, -1 squared is 1, and the square root of 101 squared is 101. So we'll have 100 over 101 minus 1 over 101 is 99 over 101. Okay, so there is the cosine of 2 theta. Now to get the tangent, we could use the tangent formula, but another way we could go about doing this, and it's going to be a little simpler, is to use a quotient identity. So we can use the fact that the tangent of 2 theta is equal to the sine of 2 theta over the cosine of 2 theta. Let me write that there. That's the sine of 2 theta over cosine of 2 theta. Okay, so that's going to be 20 over 101 divided by 99 over 101, or 20 over 101 times 101 over 99. Since dividing is the same as multiplying by the reciprocal, we have a 101 on top and bottom that cancel, and this is going to reduce to 20 over 99. Okay, so you may see problems like this in ALEKS where you're being asked to use a formula to find sine, cosine, and tangent of something. And just keep in mind, because of our quotient identities, we don't have to use the formula for tangent. We can just use the formulas for sine and cosine, and from there divide them to get the formula for tangent. So those are the two main examples for double angle formulas. In the next video, I'll take a look at some formulas that we can derive from the double angle formula for cosine.